Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on MathBase, of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. You step on inside, please. Take attendance. Mark you here. We are dealing with we did rational expressions, multiplying and dividing them, then adding and subtracting, which I thought was more proper order than kind of the other way around. Now we're going to be solving rational equations, and I think it has more to do with the adding and subtracting, so this is a good segue from the last one, because we got to find some common denominators, and most of this will go pretty briskly if you knew what was happening before. So you had to have known what was happening before to make sense of this. Find a common denominator. And what we're going to do now with an equation is we don't need to simplify it and keep it as a fraction if we don't want to. We can totally just kind of clear the denominator. I'm going to start you off with the property, and I'm going to show you the practice problems just straight up right now. Here's an idea, guys. If we have two fractions that are equal to each other in the way that they're both dividing by the same thing, like a common denominator, then that means that we can just not annex the denominator, guys, but multiply both sides by the denominator's value, which of course clears it out. A would then equal B. Now, one thing you have to be careful of is saying that hopefully you were never dividing by 0, because if that's the case, well then, this doesn't really work the way that we want it to. We'd be multiplying by 0, dividing by 0. It's not really going to work. So one of the things with this, guys, is when we solve for x in situations, we got to make sure that, as before, the x solution does not have us dividing by 0. Now, there's one thing with these problems, guys, which I'm not going to do in this video, and I wish I was. I honestly is we're not doing the word problems with these where we set them up this way, and it's not solving them that's fun. It's setting them up and having the idea that we can do them this way that is fun. Something where you combine rates and say, if you can paint a house in this much time, and he can paint a house in this much time, how long will it take to do it together, or clean a kitchen together? And there are two trains going in these directions. Where will they meet? Things like that. Those kinds of questions can be solved with rational equations. We're not doing them in this video. If there is demand, or if there are requests for it in the comments section, if there are enough, I will do them, especially if you need support for it for your math class. My classes aren't doing it. It just has to do with the pace that we're at. The transformations of quadratics and cubics and stuff took up too much time for us to do anything like that. And I want to get to the graphing stuff as well. It's too bad we're not doing them. But these things, if you ever get them set up, this is how we could solve them. All right, guys, I'm going to jump forward with this. We're going to solve these things algebraically. 9 over 4x minus 5, 6 equals negative 13 over 12x. Now, all these help to kind of do a rewrite for these, because in finding a common denominator, well, actually, what I'm going to do is I'm going to factor these. And you're going to ask, how do you factor 4x? One thing I've kind of shown with my students that I think is important, that has to do with the ones that we did before, is you want to find what's missing to see what you want to multiply left. I'm going to do the prime factorization of 4, 6, and 12. 4 is 2 times 2, and there's an x there. 6 is 2 times 3. And again, these are the prime factorizations. 12 is 2 times 2 times 3. Once again, a prime factorization. If I do a prime factorization, then I know what's missing in the other terms, because I want to get a common denominator. I want to know what's missing in the other guys, so I can go ahead and multiply by those. For example, this 2 times 2 times 3 times x, it looks like this denominator is fulfilled with all the other things that this has. This clearly has 2 2's, this has a 3, it has an x. So I don't need to multiply this denominator by anything else. But this one has 2 times 3. It doesn't seem to have an x or another 2. So I'm going to multiply top and bottom by that 2 and that x right there. This 2 times 2 times x seems to be missing a 3 that this and this have. So I'm going to multiply this top and bottom by 3, as you can tell. So if I were to give like the full effect version of this now, on bottom of all of these, 2 times 2 times 3 is 12, times x is 12x. This has a common denominator here, guys, of 12x. So I've achieved that common denominator here by writing that. Do I need to write it that way? No, not necessarily. It's up to you. In fact, at some point here, I'm about to get rid of the denominator. But on top, I have 3 times 9, which is 27, 2x times 5, which is 10x, and a negative 13. So here was the idea. Here was the idea with this property that we used. Now we have a common denominator and an equal comparative value. If everything is divided by the same thing, I could multiply both sides by 12x. And what's going to happen is 12x, and I'm not going to write this next time, But if I multiply this by 12x and multiply this by 12x here, 12x divided by 12x is gone, 12x divided by 12x is gone, 12x divided by 12x is gone. You're left with just what was left on top, which is 27 minus 10x equals negative 13. Hey, now we can solve for x in a fun and clean way, if you don't mind here. So I'm going to, I'll keep the negative 10x here. I'm going to subtract 27 from both sides, and I get negative 10x equals negative 40. And divide both sides by negative 10, and I get x equals 4. And that would be my solution. X equals 4. If I said negative 4, sorry. X equals 4. Now, in previous videos, guys, we had referred to restrictions. We had referred to things saying like, hey, you got to make sure that you're never dividing by 0. And that's true. You got to make sure you're never dividing by 0. So if it came to restrictions here, one thing that we would be stating at the time is, what values would give you 0 when you plug in x? Well, if x equaled 0, 0. We could say x cannot equal 0. And I understand you writing that, but listen, before we were simplifying a fraction, something that was equivalent to some expression, and stating that in this expression, you cannot plug in these values for x. But here's the thing, guys. We weren't simplifying an expression. We sort of were. But our goal was to solve for x here. Our goal was to find out what value or values of x would give me a true statement. Plug in x equals 4 into here. What would give me left side equals right side true statement stuff? And the answer is 4. Now, I know that we're saying x can't equal 0, and it's something we're going to have to pay attention to. We got to get the idea of, hey, is this a 0? No. Okay, then we're good. X equals 4. 4 is fine to plug into here. When I plug in 4, I don't divide by 0. And that's all that I care about. That's all that I care. I don't care that x can't equal 0. You know what else x can't equal? X also can't equal 1. You might be saying, but Mr. Robinson, if I plug in 1 for x, I don't care that you don't divide by 0 here. It doesn't give you a true statement. The only statement that works here, x can't equal 2, 4.1, 1,000. The only x value that works in this thing is 4. The restricted value, of course, wouldn't work, but nothing will work here except for 4. The only thing I care about is, does my solution work? And if that doesn't work, if this solution would be a restriction, I would omit it. It would be what's called an extraneous solution. And we're going to run into them. It would be what's called an extraneous solution, and we'll get rid of it. So x can't equal 0, I don't care about. I don't. I care, do my solutions work? And that's the only thing I care about. So that's the difference between equations and expressions. The other different thing between equations and expressions, I hope this makes sense, guys, is that when I eliminated the denominator here, that was because this is an equation. I can multiply both sides by the same thing all I want, just like I subtracted 27 from both sides here, and just like I divided both sides by negative 10 here. I can do anything to one side of an equation as long as I do it to the other side, and it keeps balanced. In an expression, I can't do that. I got to keep the original expression, the new expression equivalent to my original expression. I can't just cancel out denominators in an expression. In an equation, I totally can. Likewise, I solved for x. 4 works because it doesn't have me divided by 0. And we're good. And we're going to see extraneous solutions not only in these rational equations, but also when we hit radical equations. We're also going to hear the word extraneous, and that'll happen. All right, let's move on to number 4. I know that was kind of a long talk for that one, and I hope it kind of clears it up for the future problems we do, now that I'm 8.5 minutes in. All right, number 4. Let's find a common denominator among these guys here, where I have 3 over x plus 1, 2 over 7, and this is 2 over 1. You know, don't forget the fact that you are dividing 2 by 1 there. All right, let's find a common denominator here. Clearly, the 1 is, you don't have to multiply these by 1, right? It doesn't change anything. So you're really uniquely looking at the x plus 1 and the 7. Well, the x plus 1 is missing a 7, and the 7 is missing in x plus 1. So let's multiply those. And of course, 1 is missing both of them. So I got to multiply by 7 and x plus 1 on that. And this will give me a common denominator. Now, at the stage, if you saw last time, guys, once I achieved common denominator status, really ultimately what I did with it was I got rid of it. So if you don't mind, here on and in the future, and again, when I say get rid of it, I mean in a mathematical way, not in a careless, I don't know what I'm doing magic step kind of way, but I can kind of treat it like a magic step now. I'm, in essence, guys, now that I've achieved what I need to get a common denominator, I wrote x plus 7 down here, I meant x plus 1. Now that I achieved what I really needed for a common denominator, the denominator is really, it's taking care of what I needed with it. Hey, let's multiply both sides by 7 times x plus 1, and they'll cancel. So now my denominator is going to be gone. All that's left is really what I care about, which is on top. Now, I still need to be careful for extraneous solutions from the original equation once I get my solution. But at this point, I'm going to ignore all that. I just need to make sure to multiply 3 with 7, 2 with x and 1, and 2 with 7, so 14. Is that okay that I say that? 14 with x and 1. Okay? So there's my setup there. Now let's solve for x. 21 plus 2 is 23. And, honestly, guys, I'm not going to sit around with this algebra. This algebra stuff is stuff you should already know. So subtract 2x from both sides, subtract 14 from both sides, divide both sides by 12, and you get x equals 9 twelfths, which reduces to 3/4. All right, so there's, sorry about that. I'm not going to spend a long time on the algebra portion. What you need is to get to this stage here. And we're going to deal with some quadratics, I think, almost immediately here, coming forward. Or pretty soon. But, like factoring. But we've done that as well. But 3/4, is that a problem plugging in? No. 3/4 plus 1? No. I'm not dividing by 0 there. That's good. 3/4 works. I'm not going to check and see if 3/4 actually works. You're going to have to take my word for it that 3/4 makes the left side equal the right side. And same with 4 over here. That's us solving algebraically. That's you trusting the math teacher. But there we got to check and see, does that solution, not did we do any math wrong, did that solution make us end up dividing by 0 in this original thing? Okay. All right, number 5. So on number 5 here, what we want to do is look to, factor. We want to take this thing and see what's missing. This is largely, honestly, I'm probably overspeaking. This goes in large part of what we did from the last video of simplifying rational expressions. And if you didn't watch it, I do a lot more explanation there when it comes to what's missing stuff. You can probably pick up what I'm talking about with this, but I'm not going to get too deep into it. Okay. Now, oh, by the way, -5 times 3 is -15, and -5 plus 3 is -2. That's how I factor that. I'm sorry. Okay, so let's find out what's missing. And, there's a plus 3, x plus 3, x minus 5. It looks like those were the factors that show up here, which is nice. You don't like to get buried into like a bunch of I got to multiply this by this. So basically, this denominator is pretty complete, given that I'm going to multiply this one by the x minus 5s to complete this one, get a common denominator. And this one, I'm going to multiply the x plus 3s and complete that one. So denominator is now disintegrated. I'm gonna not write it anymore, and I'm gonna focus on the top. 56 is still a 56 here. Now here's something I mentioned in the last video. This is a -6 distributing into here. It's not just a 6. This will trip up so many people, and I'm trying to give you the warning now as I gave you before. -6 times x, -6 times -5. This is not -6x minus 30. It's -6x plus 30. That is a negative. This is a quantity. This is a quantity. Treat this as a -6 best as you can. 7 times x, 7 times 3. And remember, denominators now in irrelevant namesake when it comes to solving for this algebraically. I got the common denominator, fulfilling the property. I don't think I need to overspeak on it anymore. I'm probably going to stop. All right, combined like terms here. I got 56 plus 30, which is 86, and 7x plus 21 here. If I add 6x to both sides and subtract 21 from both sides and divide both sides by 13, I get x equals 5. Now, you look at 5 and you state, well, okay, if I plug in 5 into here, and maybe you don't want to spend time here, check this one out. You plug 5 here, it's not a problem. You plug 5 here, it is. 5 minus 5 is 0. You get 7 over 0. It doesn't matter if you don't here or here, which you would here, by the way. You divide by 0 there. X equals 5 is a problem. X equals -3 would have been a problem as well if -3 was one of my solutions. It's not, so I don't care about it. But 5 is, and I care about that. It doesn't work. This is called an extraneous. I've got to spell extraneous with an X. This is called an extraneous solution. So x equals 5 was my only solution opportunity. It's not a solution, so what is? If there are no solutions left, then the answer is exactly that. There is no solution. There is no value of x that I can substitute into the original equation to make the left side equal the right side. 5 was my only shot, and it didn't work because you ended up dividing by 0. And now look, you might be asking, why did 5 even show up in the first place if it doesn't work? The idea really is that before this was a rational expression or equation, now it's not. We solved x equals 5 for this. Not for this. Clearly what's supposed to be here is supposed to be here. But remember what we talked about before. If A over C equals B over C, then A equals B, provided that C didn't equal 0. Well, C, if you plug 5 into here, that's an example of C equaling 0. And that's the only thing that would have worked, but it just doesn't. This doesn't know that division by 0 ever happened. A equals B doesn't know that division by 0 didn't ever happen. You know, that's kind of the construct of this. That's kind of what causes that to be what it is. So I hope that kind of makes sense. All right. Number 6. Oh, by the way, how many problems am I doing? I did 3 problems there. I have 1, 2, 3 problems here, 4, 5. And these ones have a little different level to them. But 3 more problems of doing kind of this algebra. And like I said, no word problems. I'm sorry. I want them. I know you don't care. You could fast forward through them. I want them. All right. So number 6 here. It's got kind of a dark green. So number 6, I got x squared minus 29. It looks like I want to factor this thing down. That's a -7 and -3. If you're not sure what I'm talking about, then you have some videos to rewind here. This is assuming you know how to factor. And by the way, x minus 7 is here, x minus 3 is here. You know, they do, and I've mentioned this before, they really do hold your hand a little bit and say, you know, you're probably looking for these. You know, you're probably looking for those terms. And that's exactly what showed up here. All right, so let's find a common denominator there. So it looks like this guy needs a little, you know, little x minus 3 on top and bottom. And this one, you know, little x minus 7 on top and bottom. And then this one is a complete denominator of both of those things. Don't really need to contribute anything else. Common denominator, ignore denominator, except for, you know, we look for extraneous solutions. So let's see. I got an x squared minus 29. Oh, where's my dark green? Where'd that go? I got an x squared minus 29 over here. And over here, I got to distribute the 6 into the x minus 3. So I got 6x minus 18. And then 5 distributes into x minus 7. And that's 5x minus 35. Okay, so that's x squared minus 29 equals 6x plus 5x is 11x. Negative 18 minus 35 is negative 53. All right, guys, this is a quadratic equation here, you know? And in a quadratic equation, given, you know, assuming it's factorable, which, you know, we're going to play it under the assumption that it is, and I think it is. Assuming that it's factorable, what we're going to do is, well, I'll do this anyway. If it wasn't, I'll probably use quadratic formula. Let's set this equal to 0. Subtract 11x over. Add 53 over. Negative 29 plus 53. 53 minus 29 is 24. Positive 24. And that's set equal to 0. Because when we factor this is totally factorable. When we factor this, we can solve using what's called zero product property. So negative 8 times negative 3, negative 8 plus negative 3. So negative 8 and negative 3 right here. If this times this equals 0, this is something we did before, then either this equals 0, x minus 8 equals 0, therefore x equals 8. This, again, I'm assuming you've heard me do this before. Or x minus 3 equals 0, so x equals 3. And those are the 2 solutions. Okay, 2 solutions provided. Now we got to check and see if either is extraneous. Can I substitute 8 into the original equation and have no problem? I mean, yeah, sure. You know, this was the factored form down here. 8 minus 7 is good. 8 minus 3 is good. 8 minus 7 is good. 8 minus 3 is good. There's no problem substituting in 8. 8 is a pure good solution. Assume that it calculates just fine. 3 is a problem. 3 minus 7 is fine, but 3 minus 3 there is not. And of course, when it factors here, 3 minus 3 is no longer good there. 3 is extraneous. You want to kind of cancel it out. Note that it was extraneous, that it was something that you discovered, but we now exclude. This is not no solution. X equals 8 works. That one's fine, but it's the only one that's going to work. 3 will not. Huh, the Rams got a field goal. All right, so there's that one there, solving number 6. Okay, and some of these problems get a little longer than the space may kind of provide, so I apologize for that. All right, number 7 and 8. So on number 7 here, let's go ahead and play our factor game. I have 2 times x plus 3 as 2 is a common factor. I have 1/6 here. It looks like they really got to multiply by something, so I'm going to give it space. And 2 over x plus 4. Nothing else to factor there. Okay, guys. You know what? I'll turn 6 into this. I'll turn 6 into 2 times 3. Really want to show you what's missing everywhere. I really want to show you what's missing everywhere. Okay. Looks like there's kind of a lot missing. This problem might get a little long. I don't know if it's going to get long, but it's going to get long in the tooth. As far as common denominator step goes. When it comes 2 times x plus 3, you can notice that it's missing the 3 that this has, and it's missing the x plus 4 that this has. So I'm going to multiply top and bottom by 3 and x plus 4. I'm sorry, that's a 4. Let me do that again. By 3 and x plus 4. You know, we got to get what every other part's missing. The 2 and 3 is missing. It has 2 and 3. It's missing x plus 4 and x plus 3. So x plus 4 times x plus 3. Again, that's a 4. Sorry about that. Over x plus... Not enough space. And then this one is missing... Oh, everything. It's missing, except for x plus 4. It's missing 2. You're saying that's a 2. No, in the denominator. It's missing 2 and 3. So 6. And it's missing x plus 3. 2, 3, x plus 3. So as far as common denominator goes, if I did, and I'll write the common denominator for you this time just to kind of show you. The 2 times 3 is 6, so it's missing 6 times x. Sorry, the common denominator is 6 times x plus 4 times x plus 3, like that. Okay. Now, I'm going to totally ignore this the next time, and honestly, I kind of regret writing it now, because not only is it taking up time, but it will take up space. All right, so the rest has got to expand on top, though, right? We got to take care of everything else. If I can help you here, 5 times 3 is 15. I got to distribute 15 into x plus 4. So that's 15x plus 60. 15 times 4 is 60. That minus there. We're going to have to be careful with that. But the 1 doesn't do anything to the x plus 4 times x plus 3, but I got to FOIL that out. So that is x squared plus 7x plus 12. And then right here, 2 times 2 is 4 times 3 is 12. So 12 is going to distribute into x and 3. That's 12x plus 36. Whew! And I need room for this other problem. Now, common denominator, guys, I don't need this part. Be careful with this minus, though. This minus will distribute into all 3 of these terms. All of those become subtraction. Okay? Every single one of those. So, let's go back to blue. So this is 15x plus 60 minus x squared minus 7x minus 12 equals 12x plus 36. Okay, this will be a quadratic. I want a positive x squared term. So I'm going to simplify this. So negative x squared, 15x minus 7x is 8x. 60 minus 12 is 48. And 12x plus 36. Okay, I want my x squared term positive. I'll go ahead and move these terms over, but I'm going to change the signs ultimately. Okay, so minus 12x to both sides is minus 4x. And minus 36 here is positive 12. So this equals 0. And now I multiply everything by negative 1. So x squared plus 4x minus 12 equals 0. All right, that cleaned up. Oh, you can't see this. I'm very sorry. There we go. Let me move myself. I forgot I was on this side of the video. All right, so my bad. So negatives, positives. No, multiply everything by negative 1, including the 0. All right, this factors down to x plus 6 times x minus 2 equals 0. Therefore, x equals negative 6 or x equals 2. Are there any extraneous solutions? I don't think so. No issues in the original. Look, the factor form would reveal it. Is there a negative 6 or 2 issue here? I don't think so. There are 2 different answers there. Either x equals negative 6 or x equals 2. 2 solutions that are satisfied. All right. Yeah, that got long in the tooth to begin with, but make sure you distribute that negative there. That's, one small mistake. Just like the long division problems. One small mistake can really mess you up. And I'm sure my students are going to watch this video for that problem. Okay. So I hope that helped. All right, number 8. You might watch it. I don't know. I haven't done these problems before. All right, number 8. I just like that they're kind of here. I think that they're valid for what we're doing. All right, 5 over... this is going to factor to x minus 2 times x minus 1. Okay? You're lucky we're not doing factoring of the bigger than, like, x 1, whatever. All right, 1 over x minus 2. Looks like I'm going to have to fill something in there. Equals, so I got an x plus 6 on top. The first time we saw x's on top, huh? Over, and a factor of 3. I'll factor the 3. Got x minus, not 3, excuse me, minus 1. Okay, so because that 3 is there, guys, that means these things are going to get 3s. So this is not even complete. This needs a whole 3 over 3 going for it, This needs the 3 and x minus 1, as these other ones have. So 3x minus 1. Whoop. And then this thing here needs the x minus 2. That's a common denominator. 3 times x minus 2 and x minus 1. All good, good, good. Let's ignore the denominator now, if I say that magically. Let's ignore the denominator as we now have 3 times 5 is 15. Okay, be careful here. Once again, 1 times, whatever, that's gone. But be careful with the minus. That is a minus. Negative 3x and negative 3 times negative 1 is positive 3. So plus 3. And now we got to FOIL that thing. So this is going to be x squared minus 2x plus 6x is plus 4x. And then minus 12. Hey, I've seen that before. Right there. Right? X plus 6, x minus 2. All right. Maybe they knew you were going to do that. And they say, all right, do that again. All right. 15 plus 3 is 18. Equals, so x squared plus 4x minus 12. Okay, this time I'm going to keep my x squared term positive. Let's add the 3x over. Let's subtract the 18 over. So that's going to be, I'm going to write them on this side though. X squared, 4x plus 3x is 7x. And minus 18, negative 12 minus 18 is negative 30. All right, so that equals 0. So let's go ahead and factor that down. Oh, I have plenty of space. X plus 10 times x minus 3 equals 0. So x either equals negative 10 or x equals 3. Okay, are these extraneous? Negative 10 can go in just fine. 3 looks like it can also go in just fine. We won't be dividing by 0. Those are our 2 solutions. So, okay, those are the ones where we solve algebraically there. I don't think these kinds of problems are that. I forget what these were. Let me see them. All right, I selected them. This went to number 8. Now I'm on number 17. This is a modified version of my workbook here. All right, number 17. Which of the following equations have at least 2 excluded values? Select all that apply. No, they didn't say extraneous solutions. They're not asking you to solve this thing. Excluded values are my same way as saying restrictions. Excluded values and restrictions are the same thing. So really, they're just having you look at it and state that, this is where we look at the what can't x equal thing without ever even solving. I'm not solving for x, despite the fact it has an equation. So let's look at what they would have here. On A, it looks like x can't equal 0, and that's the only thing that x can't equal, because you'd be dividing by 0 there. That doesn't have 2 excluded values, so it's not A. You're listing the restrictions anyway, whatever. B, looks like x can't equal 2 or 0. I'm going to put 0 first. X can't equal 0 or 2. B seems one with 2 excluded values. It says at least 2, so more than 2 would also be fine. So, right, it's all about dividing by 0 in those instances, even if something would cancel. C, x can't equal 6. And it looks like that's it. You might wonder about this one. You factor out the 2, you get x minus 6 right there. So, yeah, x can't equal 6, not C. That's not a problem there. D, okay, I have to factor this thing. X squared minus 10x plus 25. Well, that's a perfect square trinomial. That's x minus 5 quantity squared. So x can't equal 5. What about over here? X can't equal 5 there as well. Little trickster, being a little tricky there. X just can't equal 5. That's the only one. D does not apply. E, x can't equal negative 2 from right there. Let's factor this one out. That would be x plus 2 times x plus 3. X still can't equal negative 2. But also x can't equal negative 3. So E does apply because 2 excluded values there. Now, I don't know what the solutions are. I didn't solve for them. They didn't ask for what are the extraneous solutions. They just said, what are the restrictions? What are the restrictions? Those are restrictions. If we solved for them, I don't know. I haven't done it. Photo method. See what the answers are. All right. And number 21. Critical thinking. Now, there was more that was asked of this thing. I don't think it would be enough for my students to know, or you guys, because I haven't graphed yet. This thing assumes you've already graphed rational functions. I think it was going to talk about domain and range, describe how you'd find the inverse. I mean, I'll describe it to you, but we'll just find the inverse here. I want to know that my students don't know how to find inverses. Now, this one might be a little harder. You haven't seen something like this before. I don't know how much rational I don't know how much this section has to do with what we're talking about. That's all I'll state. It's just that we've been practicing inverses before. This is a rational equation, so we'll just do it. I don't know how much I want to explain the graph stuff. It has to do with asymptotes. Probably won't explain the graph. I'm just going to find the inverse for you, okay? So let's change f of x into y, and then I'm going to swap the x and y. So swap x and y, you'll get x equals y minus 1 over y minus 2. And our goal is to solve for y. This is where things get tricky for people. I have y's in multiple places. By the way, this does not cancel as y over y. That's not what we do. I'm going to multiply both sides by y minus 2. Just like if there's one thing to match with what we're doing here, I want to get rid of fractions. And I need to, to solve for y, I need to get y up in the numerator. So I'm going to multiply both sides by y minus 2. It's gone there. And we could talk about restriction ideas. They are talking about, see, notice how they said x can't equal 2? Of course not, because you divided by 0. So we could talk about restriction things. I'm fine with that. But our goal is to solve for y. So I have x times y minus 2 equals y minus 1, right? Now, how do you get y by itself when it does this? Here's what you want to do. You do want to distribute. You want to distribute x into the y in the negative 2. We'll get xy minus 2x equals y minus 1. Now, here's why you want to do it. I want to get all y terms on one side of the equation, construct y as a common factor, and factor that out of those two terms, and then I can divide by the remaining quantity. What do I mean by that? What I mean is, let's go ahead and move this. I'll go ahead and move this y to this side of the equation. Now, I'm going to subtract y over here. It's not going to combine with it. I'm not going to combine it with anything. I'm just going to subtract y. I do, however, need to move it because I'm going to add the 2x over. So let me do that again. I'm going to subtract y to this side of the equation. Not going to combine. And then I'm going to add 2x to this side of the equation. Of course, nothing would combine there. Now, here I have xy minus y on this side. And on this side, I have 2x minus 1. So why does this help me? Because y is now a common factor in both terms. And if I factor y out of here, I get x minus 1. And now x minus 1 is what's multiplying with y. So what I can do now is I can divide both sides by x minus 1. And x minus 1 is gone. And now I have y equals 2x minus 1 all over x minus 1, like that. No, x minus 1s don't cancel, nothing like that. But that would be, I'm sorry, let me call it an inverse. Inverse of x is 2x minus 1 over x minus 1. And I'd be happy to show you these graphs on a different day. And the thing here is x can't equal 1. I could talk a little bit about domain. You won't know anything about it. But, well, okay. Well, here's the domain restriction. I'm not going to talk about range restrictions. You know what? I will talk about range restrictions because it doesn't have to do with the graph. I don't have to talk about the graph with it. Here's the thing. If this domain was that x couldn't equal 2, and we took an inverse, then the domain here becomes the range here. It's kind of nice. If this domain says x can't equal 2, the range here is that y can't equal 2. And this means nothing to any of my students until they graph it. If you've graphed these functions before, then you might know what I'm talking about regarding a horizontal asymptote. And of course, vertical asymptote. Now, this domain was x can't equal 1. You know what's true about this graph up here? The range is that y can't equal 1. Kind of an interesting notion there. And I think that's something else they wanted to talk about. That's how you find the inverse. What I wanted to talk about was the algebra there. All right, guys, that's all I'm going to do for this stuff here. I do wish that I was doing the word problems, but you know what? Save it for a different video. If you request it, fantastic. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and I'll see you in the next one when we start graphing rational functions, unless I do a mixed review of the rational expressions where I multiplied, divided, added, subtracted, and of course, solved these. You'll see me graph next. That'll do it for this one. This is Mr. Robinson. Thank you so much. Take care.